Here's our first example on sketching the graph of an exponential function. Here's my function. Before we start sketching, it's important to see what the base is. Remember, the base is the number that has your exponent here. That's your base. Remember, the base had to be greater than 1 if it's an increasing function, between 0 and 1 if it's a decreasing function. So in this example, I want to know if this is increasing or decreasing. And to determine that, increasing or decreasing. To determine that, we look at A. If A is greater than 1, it's increasing. If A is between 1 and 0, it's decreasing. So for this example, it is increasing. And why do I need to know that? Because I need to have an idea of what the general form. This is the parent function, an increasing exponential function. That way I know that my graph will need to look something like this. Okay, just as reference. The second thing I want to know is my y-intercept. For y-intercept, you already know that you evaluate the original function for x equal to 0. So anywhere there's an x, you plug in a 0. And there you are. 3 times 2 to the 0 minus 2 power plus 4. That equals 3 times 2 to the negative 2 power plus 4. And that equals 3 times, remember, if we have a negative exponent, what you do is you bring that down to the denominator and it makes a positive exponent, plus 4. And that equals 3 times 1/4, right? Because 2 to the second power is 4, plus 4. And 3 times a fourth is 3/4 plus 4. And we need to look for a common denominator, which is 4. So this is equal to 3/4 plus 16/4. And now I can add these two fractions, and that gives you 19/4. And that's where your y-intercept is. And if we change this into a mixed number, this becomes 4 and 3/4. So your y-intercept is at 0, 4, and 3/4. Okay, that's your y-intercept. Okay, so far so good. Now we're going to go and find my horizontal asymptote. Your horizontal asymptote. Now, let's think about this a little bit. I have x minus 2 here in my exponent. That means I have a horizontal shift in my graph. In the parent function, this will shift my parent function either to the right or to the left, okay? And notice if I move this to the right or to the left, my horizontal asymptote for the parent function, which is at the y equals 0 line, it doesn't go anywhere. It does shift to the left or to the right, but it's still there at the y equals 0 value, okay? Now, when I multiply by a 3, the horizontal asymptote doesn't change either. But when I add 4 here, that means I move my parent function up 4 units. And the parent function will move up along the y-axis 4 units along with your horizontal asymptote. So your horizontal asymptote will also shift up. Okay? So in class, a lot of you had said, well, my horizontal asymptote is always going to be this number, plus 4. And we also had a different analysis in class. We had started putting, we would substitute values of x here, negative x values, very large negative x values here. And we said the bigger the x value negatively, then this fraction will approach 0. And 0 times 3, that gave you 0. And 0 plus 4 will give you 4, and that is the value that the function will approach when I'm very far away from 0 on the negative x-axis. That's what we said in class. But for now, your horizontal asymptote will be that very last number you have on this whole expression. It's your vertical translation, okay? So horizontal asymptote is at y equal to that number here, to 4, okay? And there you have it. Now we're going to start sketching. First thing I'm going to plot on this graph is my y-intercept, 0, 4, and 3/4. 1, 2, 3, 4, and 3/4. That's almost 5, right there. The other thing I'm going to draw here is my horizontal asymptote. My horizontal asymptote is at y equal 4. 1, 2, 3, 4. And I'm going to draw a dashed line to represent the horizontal asymptote. There it is, okay? And now I am going to look at my function should be increasing, okay? And I know I've moved my parent function up 4 units. So that means I'm up here. Here is my y-intercept at 0, 4, 3/4. And I'm approaching the horizontal asymptote as x gets farther away from 0 on the negative x-axis. So it's going to look like this function here that I drew initially that I knew was increasing. So I'm going to mimic that behavior. So I'm very close to, I cross my y-axis at this point. It is increasing, and then I'm closer and closer and closer to this asymptote. So more or less like that. Whoops, right here. Okay, there's your graph. Now, if I ask you for domain, what is the domain of this function? I'm asking you what x values are valid for this function. And notice all these x values that I'm marking here, all of them have a corresponding y value. All of them will have a corresponding, even these way up there in infinity will have a corresponding y value. So that means all these x values are contained in this graph. So that means all real numbers are your domain. If I say range, what is the range? Range is your y value. So if I sweep across this graph, I always start at the bottom, okay? When we do x-axis, we go from negative to positive. So this number here that I wrote, all real numbers, I can also write this as from negative infinity to infinity. These two things are equivalent. When I talk about range, as I was saying, I sweep from negative infinity all the way up. And notice down here at negative infinity, there is no graph. So these values are not included in my range. When do the values for y start in this graph? They start right after this asymptote. Right above this asymptote, I start hitting my graph. So my y values start at the value of 4. And notice I drew an open parenthesis because 4 is your horizontal asymptote, which is not included. And if I keep sweeping, I will have y values all the way up to positive infinity. So from 4 to infinity is my range. I hope you understood this example, and if you didn't, go back, try it on your own, and then look back at the video and see if you get the same thing. Have fun, and now I'm going to do another video with another example using reflections. I'll see you in the next video.